Event Sourcing Unleashed: Patterns, Practices, and Real-World Implementation. Welcome to the event-driven world. Why event sourcing? In the vast landscape of software development, most applications are designed around a fundamental principle: managing state. We build systems that store the current reality of our data, a user's current email address, the current quantity of an item in stock, or the precise balance of a customer's account right now. This approach, often encapsulated by the acronym CRUD, create, read, update, delete, is familiar, effective, and has served us well for decades. But what if we told you that this widely adopted paradigm, while excellent at telling you what your data is, often falls short in explaining why it is that way? Consider a common scenario. A critical bug causes some user account statuses to unexpectedly revert. In a traditional database, you might observe that user X's status is inactive, and its audit log indicates it was last updated yesterday at 3:15 p.m. by the system. But what was it before? Who or what initiated that change? And crucially, why did it happen? Without a comprehensive historical record, answering these questions becomes a painstaking, often impossible, forensic exercise, requiring you to sift through disparate log files and piece together fragments of information. The path that led to the current state is often overwritten, leaving a frustrating void in your understanding. This is where event sourcing steps onto the stage. It offers a paradigm shift in how we think about, store, and understand our data. Instead of merely capturing the current state, event sourcing proposes that we capture every meaningful change, every action, every decision, every fact as an immutable, time-stamped event. Think of it less as saving a snapshot and more like meticulously recording every stroke of the brush that comprises a painting. The final painting is the current state, but the series of brushstrokes tells the full, undeniable story of its creation. To truly grasp this concept, let's consider a familiar analogy: a bank account. When you check your bank balance, you see a single number representing your current funds. However, that number isn't stored directly, it's derived. Your bank account's true source of truth isn't your current balance, but rather the exhaustive, chronological list of every deposit, withdrawal, and transaction you've ever made. Each one of these transactions is an immutable event: deposit made, withdrawal processed, fee charged. To determine your current balance, the bank simply sums up all these events from the very beginning. If you want to know your balance from last month, or audit a specific charge, the bank doesn't have to magically rewind. It simply refers to the ledger, the complete, unchangeable record of every event. This bank ledger illustrates the core principle of event sourcing. At its heart, event sourcing is an architectural pattern where all changes to application state are stored as a sequence of immutable events in an append-only log, commonly known as an event store. Instead of storing just the final outcome of an action, event sourcing focuses on storing the facts: what happened, when, and with what data. These facts, once recorded, are never altered or deleted. They form the complete, indelible history of your system. So, why embrace this profoundly different approach? The benefits of event sourcing extend far beyond mere historical preservation: complete audit trail and compliance. Every single change, every decision, and every interaction is captured as a distinct event. This unwavering record provides unparalleled auditability, making it effortless to understand precisely what happened leading up to any specific state. This is invaluable not only for internal accountability, but also for regulatory compliance, offering an undeniable sequence of truth. Temporal queries and time travel. Because you possess the full history, you can reconstruct the state of your system or any specific entity within it at any point in time. Need to see what a customer's shopping cart looked like 5 minutes before they abandoned it? Want to understand how a product's price evolved over the last year? Event sourcing makes these temporal queries possible by simply replaying events up to the desired moment. This time travel capability is a debugger's dream. Simplified debugging and issue playback. When a bug surfaces in a traditional system, reproducing the exact conditions that led to it can be a nightmare. With event sourcing, you have the exact sequence of events that generated the buggy state. You can literally replay that sequence, isolating and debugging the issue with remarkable precision. This transforms troubleshooting from detective work into controlled experimentation. Enhanced scalability and read flexibility. Event sourcing naturally pairs with a powerful concept known as Command Query Responsibility Segregation, or CQRS. This allows you to separate the right model, the event store, and your business logic for processing commands from the distinct read models, optimized views of your data designed for specific query needs. This separation enables independent scaling and optimization of reads versus writes, leading to highly performant and adaptable systems. Rich business insights. The stream of fine-grained events is a goldmine for business intelligence, analytics, and machine learning. Unlike aggregated, current-state data, events provide the raw ingredient for understanding user behavior, identifying trends, and making informed business decisions. For example, by analyzing product-viewed event sequences, you can build sophisticated recommendation engines. To illustrate the stark difference between CRUD and event sourcing, let's revisit a simple action: a user changing their password. In a traditional CRUD system, when a user updates their password, the database record for that user is typically updated in place. The password hash field for that user is simply overwritten with the new hash. The old password hash is lost forever. If you later need to know if a user has changed their password frequently, or when their last password change occurred, you might only rely on a separate last updated timestamp field, which doesn't specify what was updated. The why and the details of the change are gone. Now, in an event source system, when a user changes their password, a unique event, let's call it password changed event, is created. This event would contain information such as the user ID, a timestamp, the new password hash, and potentially the old password hash for auditing. Crucially, this event is appended to the user's event stream in the event store. The original hash remains part of the historical sequence of events. If the user's password is later reset by an administrator, an admin password reset event would be recorded. The history is vibrant and complete. You can reconstruct their password history, observe the frequency of changes, and even analyze who performed the action, all by simply replaying or querying the immutable sequence of events. You might be thinking, this sounds more complex than just updating a database field. And you'd be right. Initially, it represents a different way of thinking about data and system design. It requires a shift from perceiving data as a static record to seeing it as a dynamic, evolving story. But this initial conceptual overhead is often dwarfed by the profound long-term benefits in terms of auditability, debugging, flexibility, and business intelligence. If the concept of rebuilding state from a ledger of facts, traveling through time to observe past realities, and unlocking rich historical insights sounds compelling, then you've taken your first step into the event-driven world. In the following chapters, we will peel back the layers of event sourcing, examining its core components, exploring the powerful design patterns that make it resilient, and guiding you through the practicalities of implementing it in real-world applications. Get ready to unleash the full power of your data's history. 2. The anatomy of an event source system, core concepts explained. In the previous chapter, we explored the why behind event sourcing, understanding its power to preserve the full history of our data and unlock capabilities unimaginable in traditional state-based systems. Now, it's time to delve into the how. How exactly does event sourcing work? What are its fundamental building blocks? Understanding these core concepts is crucial for grasping the mechanics of an event-sourced application and preparing you for the design patterns we'll uncover in later chapters. At its heart, an event-sourced system is comprised of 4 primary components: events, commands, aggregates, and the event store. Let's dissect each one. Events, the immutable truth. If event sourcing has a heartbeat, it's the event. Events are the bedrock, the core around which everything else revolves. An event is merely a record of something that happened in the past. It's an immutable, undeniable fact. Once an event occurs and is recorded, it cannot be changed or deleted. Think of it this way. If a customer called your support line because their order status was incorrect, the event order shipped event happened, or it didn't. It's a statement of fact, not an instruction or a request. This past tense indicative nature is essential. They are typically named in this manner, such as order placed, item added to cart, payment processed, or user registered. Each event is a self-contained data package and typically includes type, a clear, concise name, like product price updated or customer registered, that tells systems what kind of event it is. This is vital for different parts of your application to understand how to react to it. Unique identifier, ID. A unique identifier for that specific event, ensuring it's never confused with another, even if two events of the same type occur almost simultaneously. Timestamp, the precise moment the event occurred. This provides crucial temporal context, allowing you to reconstruct history accurately and chronologically. Payload, the essential data that fully describes what changed as a result of this event. For a product price updated event, this would include the product ID, the old price, the new price, and the currency. The key here is that the payload describes the fact, not an instruction or an expectation. Metadata, optional but highly recommended. Contextual information that enriches the event without being part of the core business data. This might include the user ID, who initiated the action, a correlation ID to group related events across a distributed system, or a causation ID, which event or command led to this specific one. The immutability of events is a powerful characteristic. It means they are a perfect source of truth, free from the worries of data corruption or accidental modification. Commands, expressing intent. While events describe what has happened, commands describe what we want to happen. A command is an imperative request to perform an action. For instance, place order command, change shipping address command, or remove item from cart command. They are typically named in an imperative style, reflecting their role as instructions. It's crucial to distinguish commands from events. A command represents an intent, a desire for a change in the system. An event represents an outcome, a fact of something that did change. A system receives a command, processes it, and if successful, one or more events are generated and stored. If the command fails validation or business rules, no events are generated. Aggregates, consistency boundaries. In any complex application, data is related. An order has order items, a customer has addresses. Keeping related pieces of data consistent is paramount. In event sourcing, this responsibility falls to the aggregate. An aggregate is a cluster of domain objects that are treated as a single unit for data changes and consistency. It's a conceptual boundary, and anything inside that boundary must always be consistent. For example, an order with its associated order items would typically form an aggregate. A customer with their addresses might be another. Each aggregate has a single entry point, known as the aggregate root. This root is the only entity that can be referenced from outside the aggregate. All commands targeting an aggregate must go through its root, which ensures that all changes within the aggregate maintain consistency rules. When you want to process a command for an aggregate, e.g., update order shipping address command for a specific order, the system doesn't just load a database record. It first needs to reconstruct the aggregate's current state. This process is called rehydrating the aggregate. It involves fetching all events associated with that aggregate, identified by its unique ID, like order ID, from the event store, ensuring they are ordered chronologically. The aggregate then replays these events onto its internal state. Each event modifies the aggregate's state as if it were happening again. Let's illustrate with an order aggregate. The system receives an update order shipping address command for order 123. It goes to the event store and retrieves all events for order 123, starting from its very beginning. The first event might be order created event, order 123, customer ID, initial address, status equals pending. The aggregate processes this, establishing its initial state. Next, item added to order event, order 123, product ID equals P1, quantity equals 2. The aggregate adds item P1 to its list of items. Then item added to order event, order 123, product ID equals P2, quantity equals 1. Item P2 is added. Perhaps shipping address updated event, order 123, old address equals A, new address equals B. The aggregate updates its internal shipping address to B and so on, for every event in the sequence. Once all events have been replayed onto the aggregate, its in-memory representation reflects its current, consistent state. Only then can it process the new update order shipping address command. If the command is valid, the aggregate will apply the change and emit a new shipping address updated event, which is then persisted. This rehydration process ensures that all business rules validated by the aggregate always operate on a complete and consistent view of its data, reconstructed directly from the immutable source of truth. The event store. The source of truth. The final critical component is the event store. This is the persistent storage mechanism for your domain events. Unlike traditional databases that store the current state, the event store is an append-only log. This means events are only ever added to it. They are never modified or deleted. Functionally, you can imagine the event store as a series of streams. Each aggregate typically has its own event stream, uniquely identified by the aggregate root's ID. When an aggregate processes a command and produces new events, these events are appended to its specific stream in the event store. Key characteristics of an event store include durability. Events, once committed, are safely stored and will not be lost. Ordering. Events within a stream are guaranteed to be stored in the order they occurred, which is vital for correct state reconstruction. Atomicity for appends. When an aggregate produces multiple events as a result of a single command, those events are committed to the event store as a single, atomic transaction. Either all of them are saved, or none are. The event store's primary role is not to be queried constantly for current state, but to act as the ultimate ledger, the complete, chronological record of every business fact that has ever occurred in your domain. Overall conceptual flow. Now that we understand the individual components, let's put them together to see the conceptual flow of an event source system. Command reception. A user or another system sends a command, e.g., place order command requesting an action. Command handling. A dedicated command handler receives this command. Its first task is to identify and load the relevant aggregate, e.g., the order aggregate. Aggregate rehydration. The command handler requests all events for that aggregate from the event store. The aggregate then reconstructs its current state by replaying all these events. Business logic execution. The aggregate, now in its current state, applies the business logic related to the incoming command. It validates the command against its internal rules. Event generation. If the command is valid and successfully processed, the aggregate generates one or more events, e.g., order placed event, item added to order event, payment pending event. Event persistence. These newly generated events are then appended atomically to the aggregate stream in the event store. This is the critical step where the state change becomes a permanent, immutable fact. Event publishing, optional but common. Once events are safely persisted, they can be published to other parts of the system or external services. This is where the power of eventual consistency and separate read models comes into play, which we will explore in the next chapter. This cycle, from command to event generation and persistence, forms the backbone of the right model in an event-sourced system. The true state of the system is not a single row in a database table, but rather the collective memory of all the events that have occurred since its inception. Understanding these foundational concepts, events as immutable facts, commands as intentions, aggregates as consistency boundaries, and the event store as the durable, append-only ledger is vital. With these building blocks in place, we can now move on to exploring how these components are assembled and utilized in powerful and flexible design patterns, starting with the indispensable partner of event sourcing. CQRS, 3 building blocks of resilience, event sourcing design patterns. With a solid understanding of events, commands, aggregates, and the event store, we can now turn our attention to the architectural patterns that elevate event sourcing from a mere persistence mechanism to a powerful foundation for resilient, scalable, and responsive systems. The most critical and almost indispensable pattern when working with event sourcing is Command Query Responsibility Segregation, or CQRS. Command Query Responsibility Segregation, CQRS. The perfect partner. You've learned that in an event-sourced system, the true state is derived by replaying a sequence of events. While powerful for maintaining a perfect audit trail and historical integrity, this approach can become inefficient for red operations. Imagine a banking application where every time a user wants to see their current balance, the system has to replay thousands of deposit-made and withdrawal-processed events. This would be incredibly slow and resource-intensive for what should be a simple query. This is precisely the problem that command query responsibility segregation, CQRS, elegantly solves. CQRS is a pattern that separates the operations that change data, commands, from the operations that read data, queries. While independent of event sourcing, CQRS is widely regarded as its perfect architectural companion because they complement each other's strengths and weaknesses so effectively. In a traditional CRUD system, reads and writes often operate on the same database schema, optimized for both. With CQRS, you create distinct models: the write model, optimized for state changes and consistency. The write model, also known as the command model, is where all the business logic resides. This is the domain we've discussed. Where commands are received, aggregates are rehydrated from their event streams in the event store, business rules are applied, and new events are generated and persisted. Purpose: to handle all state-changing operations, enforce business rules, and maintain transactional consistency within the aggregate boundaries. Characteristics: focuses on the domain, often highly normalized, though events themselves are denormalized facts, and optimized for rapid writes and the append-only nature of the event store. Components: commands, command handlers, aggregates, and the event store. When a command is processed, events are committed to the event store. Once an event is successfully stored, it can then be published to other parts of the system or to mechanisms that will build the read models. The read models, optimized for querying and display. The read model, or query model, is a separate representation of the data, specifically designed and optimized for querying and display purposes. These models are typically built asynchronously by consuming the events published by the write model. Since they are separate, they can take any form best suited for the specific query, whether that's a traditional relational database, a NoSQL document database, a graph database, or even just an in-memory cache. Purpose: to provide fast, efficient, and flexible query capabilities for various user interfaces, reports, or integrations. Characteristics: often highly denormalized, optimized for specific access patterns, and can be specialized for different query needs. They are eventually consistent with the write model. Components: event handlers, sometimes called projectors, various database technologies optimized for reads, e.g., Elasticsearch for search, PostgreSQL for reporting, Redis for caching, and specific data models to support UI displays. How read models are built from events, projections. The process of building a read model from events is often called projection. An event handler, or projector, subscribes to the stream of events published by the event store. When it receives an event, it transforms that event's data into a format suitable for the specific read model it manages, and then updates its dedicated read-optimized database. Let's revisit the e-commerce scenario from Chapter 1. The core event-sourced write model accurately maintains every single change to an order item added, address changed, payment made, all stored as immutable events. However, to display a simple My Orders list to a customer, replaying all events for every user's every order would be incredibly slow and inefficient. This is where a read model comes in. An order history projection service subscribes to all order-related events published by the event store, e.g., order created event, order shipped event, order canceled event. When it receives an order created event for order at ABC, it inserts a new document into a NoSQL database, like MongoDB or Redis, optimized for fast lookups by customer ID. This document contains summary details like order ID, status, total amount, order date, and customer name. When an order shipped event arrives for order at ABC, the projection service updates the corresponding document, changing its status to shipped and adding shipping date. If a refund issued event arrives, the projection will update the order's status to refunded and perhaps add a refund amount. This separate, denormalized custom order history collection is then used for lightning-fast queries for the My Orders view. The UI queries this specialized read model directly, never touching the event store for read operations. This design flexibility is a core benefit. You can create as many specialized read models as your application demands, each tailored for optimal query performance. Advantages of CQRS with event sourcing. Scalability. Read and write models can be scaled independently based on their respective loads. If reads are significantly higher than writes, you can add more read model instances without impacting the write system. Performance. Read models can be highly optimized for specific query patterns, leading to faster data retrieval for users. Flexibility. Different persistence technologies can be used for different read models, allowing you to choose the best tool for each specific querying need, e.g., a graph database for relationships, a search engine for full-text search. Evolvability. Changes to query requirements, e.g., a new UI feature, often only require updating or creating a new read model without impacting the core write model and its business logic. While CQRS introduces eventual consistency between the write and read models, i.e., a newly issued command might not be immediately reflected in the read model, though typically the delay is milliseconds. Its benefits often outweigh this trade-off for complex, high-performance systems. Snapshots, optimizing aggregate rehydration. The process of rehydrating an aggregate by replaying all its events from the beginning can become prohibitively slow if an aggregate has accumulated a very long event stream, e.g., tens of thousands of events. Imagine a highly active bank account aggregate with millions of transactions. Replaying all of them for every operation would be a performance bottleneck. This is where the snapshot pattern comes into play. A snapshot is a serialized representation of an aggregate's state at a particular point in time. Instead of always replaying all events from the very beginning, the system can periodically save a snapshot of the aggregate's current state. How snapshots work. Periodically, e.g., every 100 events or at certain logical checkpoints. When an aggregate has processed a sufficient number of events, its current state is serialized and saved as a snapshot into the event store or a dedicated snapshot store. When the system needs to rehydrate an aggregate, it first attempts to load the latest snapshot for that aggregate. Once the snapshot is loaded, the aggregate is restored to the state recorded in that snapshot. Then, only the events that occurred after that snapshot was taken are loaded from the event store and replayed onto the aggregate. This significantly reduces the number of events that need to be replayed, speeding up the rehydration process. For our highly active bank account, instead of replaying 1,000,000 events, we might load a snapshot from yesterday and replay only the events from today. Snapshots are purely a performance optimization. They don't change the fundamental fact that the event store remains the ultimate source of truth. If a snapshot is corrupted or lost, the aggregate can always be fully reconstructed from its complete event stream. Event publishers' subscribers. Event sourcing inherently promotes a decoupled architecture through the use of events. Once events are successfully persisted in the event store, they are typically published to various event subscribers or event handlers processors that react to them. This forms the basis of highly flexible, reactive systems. Event publishers, the mechanism responsible for making newly committed events available to other interested components. This could be a direct push from the event store, a message broker like Kafka, RabbitMQ, or cloud-based queues, or a polling mechanism. Event subscribers, any component or service that consumes these published events to perform a specific task. This includes read model projectors, as discussed, to build and update query-optimized views. Sagas process managers, to orchestrate complex, long-running business processes across multiple aggregates or services. More on this in the next chapter. Integration services, to send updates to external systems, legacy applications, or third-party APIs. Analytics reporting tools, to feed data warehouses or business intelligence dashboards. A critical consideration for event subscribers is idempotency. Because events can sometimes be delivered more than once, e.g., due to network retries, failures, or scaling of subscriber instances, an event subscriber must be designed to process the same event multiple times without causing side effects. Techniques include tracking processed event IDs or ensuring that the operation itself is naturally idempotent, like updating a value to a specific state, regardless of its current state. Conclusion: These design patterns, CQRS, snapshots, and the publish-subscribe model are not merely optional add-ons to event sourcing. They are pivotal for unlocking its full potential. CQRS empowers you to build highly scalable and performant systems by separating read and write concerns. Snapshots ensure that even aggregates with voluminous histories remain responsive. And the publish-subscribe model fosters a loosely coupled, event-driven architecture that is inherently flexible and extensible. In the next chapter, we will delve into even more advanced patterns, such as Sagas, to tackle complex business processes and manage the evolution of your event-sourced system over time. For beyond the basics, advanced event sourcing patterns. In the preceding chapters, we've established the core machinery of event sourcing and the vital role of CQRS and other foundational patterns in making it practical. However, real-world applications are rarely simple. They involve complex, multi-step business processes that span multiple components or services, evolve over time, and require careful handling of schema changes. This chapter dives into advanced event sourcing patterns that address these challenges, empowering you to build truly robust and adaptable systems. Sagas and process managers. Orchestrating complex workflows. Many business processes are not simple, single-transaction operations. Think about an online course enrollment system. A student enrolls in a course. The system reserves a seat for them. Their payment is processed. Access to the course materials is granted. A welcome email is sent. Each of these steps might involve different services or aggregates, e.g., a course aggregate for seat reservation, a payment service for processing, a user aggregate for access, an email service for notifications. Managing the flow, ensuring all steps complete, and handling failures, e.g., if payment fails, the seat needs to be released, can become incredibly complex in a distributed environment. This is where Sagas, also sometimes called process managers, come in. A saga is a long-running transaction that manages a sequence of local transactions, operations within a single service or aggregate, orchestrating a complex business process across multiple services or aggregates, maintaining eventual consistency. How sagas work. A saga listens to events from various parts of the system and, based on these events, issues new commands to initiate subsequent steps. They maintain their own state, which represents the current phase of the long-running process. Let's trace the online course enrollment example with a saga. A student initiates a enroll-in course command. The course enrollment saga starts when it receives student-requested enrollment event. This event is emitted by the student aggregate after processing the enroll-in course command. Upon receiving student-requested enrollment event, the saga, now aware of a new enrollment process, proceeds to the next step. It issues a reserve course seat command to the course service. The course service processes this command and emits a course seat reserved event if successful or course seat reservation failed event if the course is full. The saga listens. If it receives course seat reserved event, it then progresses. It issues a process payment command to the payment service. The payment service processes this command and emits payment processed event or payment failed event. Again, the saga listens. If it receives payment processed event, it issues an assign course access command to the learning platform service. The learning platform service processes and emits course access assigned event. Finally, upon receiving course access assigned event, the saga concludes that the enrollment process is complete and perhaps issues a final send welcome email command to an email service. Handling failures, compensation. The true power of sagas lies in their ability to manage failures. What if the payment processed event is not received, e.g., payment fails, or the payment service is down? The saga, designed for resilience, would receive a payment failed event or timeout if no response is received. Execute compensating actions. In this case, it would send a release course seat command back to the course service to free up the seat that was initially reserved. This ensures that resources committed earlier in the process are rolled back if later steps fail, maintaining overall consistency. Sagas are crucial for orchestrating distributed transactions in microservices architectures built on event sourcing, as they help achieve eventual consistency without relying on two-phase commits or other blocking protocols. Event versioning and upcasting. Over the lifetime of an application, it's almost inevitable that the schema of your events will need to evolve. You might need to add a new field, rename an existing one, or even restructure the event payload entirely. Since events are immutable and persisted indefinitely, simply changing the code that generates them isn't enough. Older events, stored in the event store, must still be interpretable. This challenge is addressed by event versioning and upcasting. Event versioning. This involves explicitly numbering or naming the versions of your events. For example, order placed event v1, order placed event v2. When you make a breaking change to an event schema, you create a new version of that event. New code emits order placed event v2. Upcasting, event migration. When an aggregate is rehydrated, it replays its entire history of events. If older versions of events, order placed event v1, and newer versions, order placed event v2, exist in the stream, the system needs a way to understand both. Upcasting is the process of transforming an older version of an event into its current, desired version during the replay process. Consider product price updated event v1, which might have contained only producted and new price. Later, you decide you need old price for auditing. You introduce product price updated event v2. An upcaster for product price updated event v1 would be a small piece of code that intercepts v1 events during replay. It would read the v1 event, perhaps look up the previous price, if available from other historical v1 events or a snapshot, and then transform it into a product price updated event v2 before passing it to the aggregate. Common strategies for handling event schema evolution. Additive changes. Prefer adding new, optional fields to events. Old code will ignore them, new code can read them. This is the simplest and often preferred method. New event types. If a change is significant, create an entirely new event type. Upcasters, as described above, to transform old event structures to new ones on the fly during replay. This adds complexity but preserves semantic equivalence. Schema registries. For very large systems, a centralized schema registry, like Confluent Schema Registry for Kafka, can manage event schemas and their versions, providing metadata and ensuring compatibility. The goal is to maintain backward compatibility, ensuring that your system can always rehydrate an aggregate from its complete event history, regardless of how event schemas have evolved. Event-driven microservices. Event sourcing naturally lends itself to the microservices architectural style. In a microservices ecosystem, services are typically organized around business capabilities, and they communicate with each other asynchronously, often through events. Loose coupling. Instead of making direct API calls to another service to query data or trigger actions, services publish events about changes within their own bounded context. Other services, interested in these changes, simply subscribe to those events. This drastically reduces direct dependencies between services. For example, an order service doesn't call an inventory service directly. It emits order-placed event. The inventory service subscribes to this event and takes action, e.g., reserve stock command. Autonomy. Each microservice can maintain its own event store and read models. They are self-contained units with a clear responsibility, simplifying development, deployment, and scaling. Resilience. Asynchronous communication via events inherently makes systems more resilient. If a downstream service is temporarily unavailable, events queue up in the message broker and are processed once the service recovers, preventing cascading failures. Business intelligence. The stream of events provides a canonical, real-time data feed that can be used by analytic services, data warehouses, and machine learning pipelines, without impacting operational databases. The combination of event sourcing and microservices leads to a highly scalable, flexible, and robust distributed system. But it also necessitates careful consideration of eventual consistency and distributed transaction management, which Sagas help to address. Idempotency in action. In any distributed system, especially one relying on message passing and eventual consistency, operations can sometimes be retried or events can be delivered multiple times. This introduces the risk of processing the same command or event more than once, leading to incorrect state or unwanted side effects. Idempotency is the property of an operation being able to be applied multiple times without changing the result beyond the initial application. Ensuring idempotency is critical for resilience in an event-sourced system. Idempotent commands. If a command is processed multiple times, it should only generate events and change state once. This is often achieved by tracking processed command IDs. The aggregate or command handler can store a list of command IDs it has already successfully processed for a given aggregate. If it receives a command with an ID already in this list, it simply ignores it. Guaranteed consistency at the event store. Most event stores enforce optimistic concurrency control, meaning that if a command attempts to append events based on outdated state, the append will fail. This prevents duplicate event application from duplicate command processing. Idempotent event handlers read models and sagas. If an event is delivered multiple times to a subscriber, e.g., due to network issues or retries, the event handler should correctly process it only once. This is fundamental for maintaining the integrity of read models and preventing duplicate actions from sagas. One common technique is to store the ID of the last processed event for any given projection or saga. If an event with an ID less than or equal to the last processed ID is received, it's skipped. Alternatively, the operation itself can be naturally idempotent. For example, set x to y is idempotent, while increment x by 1 is not. While seemingly a detail, building idempotency into your system from the ground up prevents subtle data corruption and elusive bugs that are incredibly difficult to diagnose in complex distributed systems. Conclusion: leveraging advanced patterns like sagas for orchestration, thoughtfully managing event versioning, and embracing the natural synergy with microservices while diligently ensuring idempotency are all crucial steps in unlocking the full power of event sourcing. These patterns move beyond basic persistence and enable architectures that are not only robust and scalable, but also highly adaptive to changing business requirements. With these tools in hand, you're well equipped to design event-sourced solutions that thrive in the demanding landscape of modern software systems. In the next chapter, we'll shift our focus to the practicalities of choosing and implementing the right event store and infrastructure for your needs. 5. Choosing your tools, event stores, and infrastructure. By now, you understand the fundamental concepts of event sourcing and the powerful design patterns that breathe life into event-driven architectures. You know that the event store is the beating heart of an event-sourced system, the immutable, append-only log that preserves every change as a factual event. But what exactly is an event store in practice? Is it a special kind of database, or can you use existing technologies? This chapter explores the diverse options available for persisting your events, along with critical infrastructure considerations to support your event-sourced application. Types of event stores. While the concept of an event store is abstract, an ordered, immutable sequence of events. Its actual implementation can vary widely depending on your project's needs, scale, team expertise, and budget. Broadly, event stores fall into a few categories: dedicated solutions and adaptations of general-purpose databases. 1. Dedicated event stores. These are databases purpose-built specifically for event sourcing. They are designed from the ground up to offer the core guarantees required: append-only writes, ordering of events, optimistic concurrency control, and stream per aggregate. Event Store DB. An open-source, high-performance, native event store. It's designed to be the central nervous system for event-source systems. Pros. Purpose-built. Optimized for event sourcing characteristics like fast appends, strong consistency guarantees within a stream, and efficient subscription mechanisms. Rich features. Built-in capabilities for projections to build read models directly within the store, subscriptions, optimistic concurrency, and stream versioning. Scalability. Designed for high throughput and can handle large volumes of events. Community and ecosystem. A dedicated community and a growing ecosystem of client libraries and tools. Cons. Learning curve. A new technology to learn and manage, often requiring specialized knowledge for optimal performance and troubleshooting. Operational overhead. Like any distributed database, it requires careful deployment, monitoring, and maintenance. Vendor lock-in. if using commercial support cloud offerings, not as widely adopted as general-purpose databases, so migration could be more involved. Axon Server. A part of the Axon framework ecosystem, Java-based, Axon Server specifically offers a dedicated event store and command bus implementation. Pros: seamless integration. Provides tightly coupled features with the Axon framework, making development significantly easier for Java projects. Distributed capabilities. Designed for distributed systems with clustering and high availability features. Cons: language-specific, primarily for Java applications, though other languages can connect via gRPC. Framework dependency, tightly coupled with Axon framework, which implies a specific architectural style. Dedicated event stores are often the best choice for greenfield event sourcing projects, especially if your team is committed to the paradigm and is willing to invest in learning a new technology for its powerful benefits. 2. Relational databases, SQL as an event store. It is entirely possible to implement an event store using a traditional relational database like PostgreSQL, MySQL, or SQL Server. You would model a single table to store your events. Table structure example. Create table events, id serial primary key, aggregated UUID not null, aggregata type varchar, 255 not null, version int not null, event type varchar, 255 not null, event data JSONB not null, metadata JSONB, timestamp with time zone default now. Unique aggregated version ensures uniqueness and ordering within an aggregate stream. Pros: familiarity. Most teams are already proficient with SQL databases, reducing the learning curve and operational overhead initially. Maturity. SQL databases are mature, robust, and have excellent tooling for backup, recovery, and monitoring. ACID guarantees. Provide strong ACID properties for transactions, simplifying atomic appends. Cons: performance at scale. While fine for initial stages, scaling an event store implemented in a single relational table for very high write throughput and large volumes of data can become challenging. Appending to a large, ever-growing table and querying specific event streams efficiently can hit limits. Optimistic concurrency. You need to explicitly implement optimistic concurrency control, e.g., using the version column yourself when appending events. Subscription mechanisms. No built-in event streaming or subscription mechanisms. You'll need to implement polling or use database-specific features, like PostgreSQL's Notify Listen, which can add complexity. No native projections. No inherent support for building projections within the store itself. Using a relational database initially is a common approach, especially for teams new to event sourcing, allowing them to focus on the domain modeling before introducing a new specialized piece of infrastructure. However, be prepared to potentially migrate as your system scales. 3. NoSQL databases as an event store. Various NoSQL databases can also be adapted to function as event stores, each with its own trade-offs. Cassandra/ScyllaDB column family store, excellent for very high write throughput across multiple nodes. Pros: extremely scalable writes, high availability, fault tolerance. Cons: complex consistency models, eventual consistency by default. No native transaction support for appending multiple events atomically to different aggregate streams. Requires client-side logic to handle distributed transactions. Complex query patterns. Best suited if you can sacrifice some immediate consistency for high availability and partition tolerance. MongoDB/DocumentDB, document database. Flexible schema often appeals to event-driven designs. Pros: flexible document structure matches event payloads well, relatively easy to scale horizontally with sharding. Cons: transaction capabilities vary by version and usually support only single document atomicity or multi-document within a single replica set. Optimistic concurrency needs careful implementation. Change streams can be used for subscriptions, but reliability varies. Kafka, distributed streaming platform. While primarily a message queue or log aggregation system, Kafka can technically serve as a durable, append-only log that fits the event store definition. Pros: incredibly high throughput, very scalable built-in replaying of messages, excellent for decoupled microservices, robust tooling. Cons, not a native event store. Lacks specific event sourcing features like optimistic concurrency control per aggregate stream or direct support for aggregate rehydration. You'd build these on top of Kafka. Stream per aggregate. While Kafka topics can be partitioned, managing a true stream per aggregate might involve many partitions or complex keying strategies, which can make consistent reads and writes for a single aggregate challenging at scale. Event storage. While durable, Kafka topics typically retain messages for a configurable period, not indefinitely. You might need a separate, long-term archival solution if permanent history is a must. Usage. Often used alongside a true event store, primarily for event distribution and building read models, rather than as the primary durable storage for domain events that back aggregate state. Infrastructure considerations. Choosing your event store is just one piece of the puzzle. The surrounding infrastructure is equally vital for a performant and resilient event source system. 1. Messaging brokers for event propagation. Once events are saved in the event store, they need to be published to event subscribers, read model projectors, Sagas, integration services. A robust messaging broker is often used for this purpose. Apache Kafka, the de facto standard for high-throughput, low-latency publish-subscribe messaging. Its distributed log nature makes it excellent for streaming events and enabling read models to be built. It also offers powerful replay capabilities for reprocessing events, e.g., for rebuilding a red model from scratch. RabbitMQ, a general-purpose message broker supporting various messaging patterns, suitable for reliable message delivery between services. Cloud-native solutions, AWS Kinesis, Azure Event Hubs, Google Cloud PubSub all offer managed, scalable messaging services. The choice of messaging broker largely depends on your existing infrastructure, scale requirements, and team familiarity. 2 database choices for read models. As discussed with CQRS, read models are tailored for specific query needs. This freedom allows you to pick the best database technology for each individual query pattern. Relational databases, SQL, PostgreSQL, MySQL, SQL Server. Still excellent for structured data, complex joins, and analytical queries if denormalization isn't enough. NoSQL databases. Document databases, MongoDB, Couchbase. Great for flexible schemas, denormalized data, and easy mapping to UI components. Key value stores, Redis, Memcached. Ideal for caching highly accessed data or simple lookups. Search engines, Elasticsearch, Apache Solr. Perfect for full-text search, faceted search, and complex analytical queries over large datasets. Graph databases, Neo4j. If your read model involves complex relationships and network analysis, a graph database might be ideal. Data warehouses lakes. For deep historical analysis and business intelligence, events from the event store can be streamed into data warehouses, e.g., Snowflake, BigQuery, or data lakes, e.g., S3, Azure Data Lake Storage. Each RED model can use a different persistence technology, optimized for its specific query pattern. 3. Monitoring and alerting. An event-sourced, CQRS-based system running on microservices will naturally be more distributed, increasing the complexity of monitoring and debugging. Distributed tracing. Tools like Jaeger or OpenTelemetry are essential to trace a single request or command across multiple services, from command origination to event persistence and read model updates. Metrics and dashboards. Track event store performance, write throughput, latency, messaging broker health, red model update lag, and resource utilization across all services. Logging. Centralized logging solutions, e.g., ElkStack, Splunk, are critical for aggregating logs from different services. Alerting. Set up alerts for anomalies, error rates, and performance degradation in any part of the event-driven pipeline. Decision matrix. Choosing your tools. The decision of which event store and accompanying infrastructure to use is rarely one-size-fits-all. Consider the following factors. Scale. How many events per second day do you anticipate? What is the total volume of historical events? Consistency versus availability. What are your team's needs for strong consistency, especially for reads, versus high availability? Acid versus base trade-offs. Team expertise. What technologies is your team already proficient with? Learning a new database adds a learning curve and operational overhead. Budget. Dedicated event stores or cloud-managed services might have different cost profiles than self-hosting. Project stage. For a proof of concept or a system with low event rates, a SQL database as a simple event store might suffice. For a high-volume, critical business domain, a dedicated event store or well-engineered Kafka setup would be more appropriate. Starting simple and iterating is often a good strategy. It's easier to migrate an event store by replaying events into a new store than to refactor an entire application written without event sourcing principles. Conclusion: the choice of specific technologies for your event store and supporting infrastructure is a critical architectural decision. Dedicated event stores offer native advantages, while general-purpose databases can be adapted for simplicity and familiarity. Regardless of your choice, a well-thought-out infrastructure with robust messaging, tailored read models, and comprehensive monitoring is paramount for building a resilient and scalable event-sourced system. With these tools in hand, the next step is to confront the inevitable challenges that arise when implementing event sourcing in the real world. 6. The roadblocks ahead. Common event sourcing challenges. Event sourcing offers a compelling set of advantages: a complete audit trail, temporal querying, unparalleled debuggability, and a natural fit for highly scalable, decoupled systems. Yet, like any powerful architectural pattern, it comes with its own set of complexities and challenges. Understanding these upfront is crucial for successful implementation and avoiding pitfalls that can derail a project. Abandoning event sourcing midway through development due to unforeseen difficulties is far more costly than acknowledging and planning for them from the outset. This chapter will illuminate the common roadblocks developers and architects encounter when adopting event sourcing. Awareness is the first step towards developing effective solutions, which we will delve into in the next chapter. 1. Mindset shift, from state-oriented to event-oriented thinking. This is arguably the biggest, most fundamental challenge. For decades, software development has been rooted in a state-centric view. Objects hold data, database tables store current values, and applications show the now. Event sourcing demands a radical change in perspective, thinking in facts, not just values. Instead of user is active equals true, it's user-activated event followed later by user-deactivated event. This requires carefully modeling domain events in the past tense, focusing on what happened, not just what the current value is. Deriving state versus storing state. Developers are accustomed to fetching an object's current state directly from a database. With event sourcing, the current state of an aggregate is derived by replaying its history of events. This conceptual leap can be difficult to internalize, especially for those accustomed to traditional CRUD operations. Impact on modeling. Domain modeling becomes significantly different. The focus shifts from identifying data fields to defining core business events and the commands that trigger them. This requires stronger domain-driven design principles. The change can feel unnatural at first, leading to awkward designs where events are merely glorified state patches rather than true domain occurrences. 2. Event semantics and granularity. Defining the right events is a surprisingly subtle art. Granularity. How specific should an event be? Should a user-updated event encompass all changes to a user, or should it be username changed event, user email changed event, user address changed event? Too coarse, and you lose fine-grained historical detail. Too fine, and you end up with an overwhelming number of event types and potential performance overhead from many small events. Event naming. Clear, unambiguous, past tense naming is critical for events. Misleading names can cause confusion and incorrect interpretations downstream. Business versus technical events. Events should represent business facts, not just technical operations. An event like database record updated event is too technical and lacks business significance. Conversely, knowing when to separate a business event from a purely technical one can be tricky. Getting event semantics wrong can undermine the auditability and historical replay benefits, making the system brittle and difficult to evolve. 3. Read model management and eventual consistency. While CQRS is a powerful enabler for event sourcing, it introduces its own set of complexities. Complexity of read models. Managing multiple read models, each optimized for different query needs, adds operational overhead. Each read model needs its own database or storage, its own projection logic, and its own deployment lifecycle. Lag and eventual consistency. Read models are built asynchronously by consuming events. This means there's an inherent delay between an event being written to the event store and its reflection in a read model. This eventual consistency can be challenging for UI/UX if not handled gracefully. Users might perform an action and not immediately see its reflection, leading to confusion. Projection errors. Bugs in projection logic can lead to corrupted or inconsistent read models. Rebuilding a read model from scratch, especially a large one, can be a time-consuming operation. Querying state versus querying history. While event sourcing excels at history, complex queries that combine current state from multiple aggregates or perform aggregate functions across large numbers of events can be challenging without carefully designed read models. Bridging the gap between the immediate user expectation and the eventual consistency of read models is a frequent hurdle. For event, schema evolution and versioning. As applications evolve, so does their domain. New features mean new events, and existing events might need to change their structure. Backward compatibility. Events are immutable, and older events will remain in the event store indefinitely. If you change an event schema, older versions of that event must still be understandable when replaying them to reconstruct an aggregate state. Upcasting complexity. While upcasting, transforming old event structures to new ones during replay, is a solution, maintaining a large number of upcasters over time can become a significant development and testing burden. Each upcaster is a piece of code that must be maintained indefinitely. Impact on read models. Changes to event schemas often necessitate changes to read model projection logic, potentially requiring read models to be rebuilt from scratch, which can be disruptive. Managing event schema evolution without breaking existing functionality or incurring massive refactoring costs is a persistent challenge. 5. Debugging and troubleshooting. Debugging in a highly distributed, event-driven system can be more complex than in monolithic CRUD applications. Distributed complexity. A single command might trigger a cascade of events, leading to updates in multiple read models and triggering actions in other services via Sagas. Tracing the flow of logic across these components, especially across different data stores and messaging systems, can be difficult. Asynchronous nature. The asynchronous nature of event processing means that problems might manifest themselves much later than the initial command, making it harder to pinpoint the root cause. Reproducing issues. While event sourcing enables reproduction by replaying events, setting up the exact environment and replaying a specific sequence of events for a complex bug needs specific tooling and discipline. Effective debugging requires specialized tools and a change in team practices. 6. Operations, monitoring, and data management. Running an event source system in production introduces new operational concerns. Event store management. Managing a dedicated event store, like EventStoreDB, adds another critical piece of infrastructure to monitor, backup, and maintain. If using Kafka, managing retention and topic configurations adds complexity. Data volume and storage costs. Event stores grow indefinitely. While storage is cheap, very high event rates can lead to massive data volumes over time, requiring careful planning for storage, archiving, and potentially cold storage. Read model maintenance. Ensuring read models are in sync, highly available, and performant requires continuous monitoring and operational discipline. The process of rebuilding read models during recovery or schema changes needs to be well rehearsed. GDPR and data deletion. The immutability of events makes right to be forgotten or data deletion requirements, like GDPR, incredibly challenging. How do you delete sensitive user data if it's permanently recorded in an event stream? This often requires creative solutions like encryption and event nullification. Data migration. If you change your aggregate logic significantly, existing historical events may no longer make sense or be sufficient to rehydrate. This can lead to complex data migration strategies. Operational aspects shift from CRUD database management to managing a distributed log and potentially many different read models. 7. Initial learning curve and team preparedness. Without proper training and a strategic approach, a team attempting event sourcing for the first time can quickly become overwhelmed. Skill set requirements. Beyond typical development skills, teams need to understand distributed systems, eventual consistency, strong domain modeling, and effective testing strategies for event-driven systems. Complexity for simple systems. For straightforward, non-auditable business domains, the overhead introduced by event sourcing and CQRS might outweigh its benefits. Applying event sourcing everywhere can lead to unnecessary complexity. The initial investment in learning and tooling can be substantial, and managing expectations and training within the team is key. Conclusion: the challenges of event sourcing are real and should not be underestimated. They require a significant investment in architectural design, tooling, operational practices, and, most importantly, a fundamental shift in how teams think about data and system behavior. However, by acknowledging these roadblocks early, designers and developers can proactively integrate solutions and best practices into their development lifecycle. In the next chapter, we will directly address these challenges, offering concrete strategies and patterns to overcome them, paving the way for a successful event sourcing implementation. 7. Navigating the complexities, solutions, and best practices. In the previous chapter, we laid bare the common challenges associated with event sourcing. While daunting at first glance, these roadblocks are not insurmountable. Many established patterns, tools, and best practices have emerged from the community to navigate these complexities effectively. This chapter reveals the solutions, offering practical advice to mitigate the difficulties and leverage the strengths of event sourcing. 1. Embracing the mindset shift, training and domain-driven design, DDD. The most crucial solution to the mindset challenge is education and practice. Dedicated training. Invest in workshops, internal knowledge-sharing sessions, and pairing when adopting event sourcing. Start with smaller, less critical projects or components to build expertise. Embrace domain-driven design, DDD. Event sourcing thrives when paired with a strong understanding of your domain. DDD methodologies encourage you to identify aggregates, commands, and events by focusing on the language and rules of your business. Ubiquitous language. Use the exact same terms for your domain concepts, events, commands, entities, in code, discussions, and documentation. This coherence naturally leads to well-defined events. Bounded contexts. DDD helps in identifying logical boundaries for your services and aggregates, which in turn clarifies what events belong where, reducing confusion and fostering loose coupling. Event storming. This collaborative modeling technique, involving business users and technical staff, is exceptionally powerful for identifying events, commands, and aggregates, and visualizing the flow of a business process. It's an engaging way to facilitate the mindset shift from CRUD to event-driven thinking. 2. Crafting events that matter. Semantics and granularity best practices. Clear, meaningful events are the cornerstone of a successful event source system. Focus on business facts, past tense. Events should always describe something that has occurred within your domain. Naming them in the past tense, e.g., order placed, payment processed, item shipped, ensures this. Avoid verbs ending in ing or imperative verbs. Granularity, the Goldilocks principle. Favor fine-grained events. Generally, more granular events, user email changed event instead of user updated event, are better as they provide richer historical detail and more flexibility for projections. However, avoid events that are too granular and have no business meaning, e.g., user first name letter changed event. Focus on business intent. An event should signify a specific business decision or state change. If an event doesn't represent a meaningful business fact, it might not be an event. Immutability. Once an event is written, it should never change. This is non-negotiable for guaranteeing historical integrity. Event enrichment. Events should carry all the data necessary for any immediate consumer to react without needing to query other services. However, avoid excessive data that might change frequently or isn't directly related to the specific event. Versioning and upcasting, as discussed in Chapter 4, additive-only changes. For event schema evolution, always try to add new, optional fields. This ensures backward compatibility without needing upcasters. Controlled upcasters. When breaking changes are unavoidable, carefully manage upcasters. Keep them simple and well-tested. Don't create an upcaster for every minor schema tweak. Event migration. For truly radical schema changes or domain redesigns, a full event migration, transforming old events into new ones in a separate process, then replaying them into a new event store, might be necessary, though this is a last resort. 3. Managing read models and addressing eventual consistency. CQRS introduces complexity, but it's manageable with proper strategies. Designing read models, fit for purpose. Design each read model specifically for the queries it needs to serve. Don't try to make one read model fit all needs. Denormalization. Embrace denormalization. Read models are often denormalized flat tables or documents, optimized for rapid retrieval rather than storage efficiency. Asynchronous updates. Understand and accept that read models update asynchronously. Tackling eventual consistency. Read your own rights. For UI/UX where users expect immediate feedback, consider strategies like using the command's generated events directly to update the UI on the client side, or optimistically updating the UI while the read model catches up in the background. A personalized read model, a copy of the relevant part of the read model for the specific user, can also be used. Lag metrics. Monitor the lag between events being written to the event store and their appearance in read models. Alerts should be set if lag exceeds acceptable thresholds. Visual cues inform the user when data might be eventually consistent, e.g., your order is processing, instead of your order has shipped. Idempotency of projections. Ensure your read model projectors are idempotent. If an event is redelivered, processing it multiple times should not corrupt the read model. This means that a projection should either be able to skip events it has already processed, or the operation itself, e.g., set x equals y rather than add z to x, is safe to repeat. Rebuilding read models. This must be a well-practiced operational procedure. Ensure your projection services can fetch all events from the beginning of time from the event store and rebuild their entire data set. This is crucial for fixing bugs in projection logic or adapting to new event schema versions. 4. Robust debugging and troubleshooting strategies. Debugging in distributed, event-driven systems requires discipline and specialized tools. Correlation IDS. This is arguably the most important troubleshooting best practice. Ensure every incoming command is tagged with a correlation ID, and this ID is propagated to all generated events, related subcommands, and logs across your services. This allows you to trace a single logical operation end-to-end through a distributed system. Causation IDs. To understand the chain of events, include a causation ID, the ID of the event or command that caused the current event command in your event metadata. Centralized logging and monitoring. Use a robust logging infrastructure, e.g., Elk Stack, Splunk, Datadog, to aggregate logs from all services. Integrate distributed tracing, e.g., OpenTelemetry, Jaeger, to visualize the flow. Event Store UI tools. Utilize tools that allow you to browse event streams, filter events, and replay specific sequences. Replay capabilities. Build internal tooling or use framework features that allow for easy replaying of specific event sequences to reproduce bugs in development environments. 5. Operational excellence and data management. Event sourcing shifts operational priorities. Event store operations. Treat your event store like any mission-critical database. Implement robust backup and recovery strategies, monitor its health, throughput, and latency. For dedicated event stores, understand their clustering and high availability features. Smart storage management. Archiving. For very high-volume systems, consider strategies for archiving old events to cheaper, slower storage. Only events relevant for active aggregates might need to be hot. Snapshots. As discussed in Chapter 3, use snapshots to reduce the number of events to replay for long-lived aggregates, mitigating rising rehydration times. Data deletion, GDPR compliance. This is complex due to immutability. Avoid storing personally identifiable information, PII, directly in event payloads if possible. If PII must be stored, encryption, encrypt PII in event payloads. The encryption key can then be deleted or revoked when data is requested to be forgotten. Event nullification redaction. Conceptually, if an event contains PII, you might be able to create a compensating event that redacts the sensitive data from future projections, or an upcaster that removes it during replay. However, the original event still exists physically. Separate PII storage. Store PII in a separate, mutable store with tight access controls, linking it to events via non-PII identifiers. When requested, delete from this separate store. 6. Managing the learning curve and initial overhead. Don't dive headfirst into event sourcing for every project. Evaluate project suitability. Event sourcing shines in complex, high-audit, highly concurrent, and evolving business domains. For simple CRUD apps, the overhead might not be justified. A composite application with event sourcing for the core domain and traditional CRUD for simpler parts, e.g., settings or lookup tables, can be a pragmatic approach. Start small. Begin with a small, self-contained business domain within your application. Gain experience before expanding event sourcing across your entire system. Frameworks and libraries. Consider using well-established event sourcing frameworks, like Axon Framework for Java, or libraries in Net like EventFlow, or in JavaScript TypeScript for Node.js environments, that handle much of the plumbing, event store integration, aggregate rehydration, CQRS dispatchers. This allows you to focus on domain logic. 7. Testing event-sourced systems effectively. Testing shifts from unit testing repository interactions to testing business logic driven by events. Behavior-driven development, BDD. Given a sequence of events when a command is issued, then a set of new events should be generated. This style naturally aligns with event sourcing. Aggregate unit tests. Test aggregates by passing them commands and asserting on the events they emit. This focuses directly on business rules. Projection integration tests test that events correctly update read models. This often involves emitting events and then querying the read model to ensure correctness. Saga integration tests test the end-to-end orchestration flow of Sagas, including happy paths and failure scenarios with compensating actions. Conclusion: event sourcing presents a fundamental shift in how we build software, and with that shift comes a new set of challenges. However, the industry has developed robust solutions and established best practices to meet these challenges head-on. By understanding and applying these strategies, from investing in domain modeling and team training, to carefully crafting events, meticulously managing read models, and embracing operational excellence, you can successfully navigate the complexities and unlock the profound benefits of event sourcing, building systems that are not only resilient and scalable, but also deeply aligned with your business. The theoretical foundations and common hurdles are now well understood. In the next chapter, we will transition towards the practical application of these concepts, focusing on how a real-world event-sourced system is architected and brought to life. 8. Architecting for success. Designing a real-world event-sourced application. With the foundational concepts, patterns, challenges, and solutions under our belts, it's time to move from theory to practical application. This chapter focuses on the architectural design process for a real-world event-sourced application. We'll consider key decisions, structure, and how the patterns we've discussed fit together to form a cohesive system. Our goal is to provide a blueprint for designing a robust, scalable, and maintainable event-sourced solution. For our purpose, let's consider a practical domain, an online learning platform. This platform will allow users to register, browse courses, enroll in them, and track their progress. This domain lends itself well to event sourcing due to its rich history requirements, enrollment history, progress tracking, complex business processes, enrollment, certification, and potential for analytics. 1. Defining the bounded contexts and aggregates. The first step in designing any complex system, particularly with event sourcing, is to apply domain-driven design (DDD) principles. This means identifying the core business areas, or bounded contexts, and within them, the key aggregates. For our online learning platform, Potential bounded contexts might include identity and access management, deals with user registration, login, profiles, roles. Course management, deals with course creation, updates, categorization, availability. Enrollment and progress, manages student enrollments in courses, tracks module completion, quizzes, and overall progress. Payment and billing, handles course fees, payments, refunds. Within these contexts, we identify aggregates, the consistency boundaries for our domain logic. Examples might include identity and access management context, user account aggregate, manages user login credentials, profile details. Course management context, course aggregate, manages details, modules, and availability of a specific course. Enrollment and progress context, enrollment aggregate, represents a student's enrollment in a particular course, tracking its status, e.g., pending, active, completed. Course progress aggregate tracks a student's granular progress through a course's modules and lessons. Payment and billing context, payment transaction aggregate, manages a single payment process. 2. Event and command modeling, the language of the system. Once aggregates are identified, the next step is to brainstorm the key business commands that can be issued to these aggregates and the events they will emit. Remember, commands express intent, events express fact. For the enrollment aggregate, an example flow might be: command, enroll student in course command, contains studented, coursed. Events emitted by enrollment aggregate: student enrolled event, initial success. Enrollment canceled event, e.g., if payment fails. Enrollment completed event, when all course requirements are met. Module completed event, emitted by course progress aggregate. Quiz graded event, emitted by course progress aggregate. This exercise, often best done through event storming, defines the vocabulary of your system and forms the contract between components. 3. Choosing the right model architecture. The right model is where your business logic lives and where events are persisted. Technology stack. This highly depends on your team's expertise. You might choose a framework, e.g., Axon framework in Java, Eventflow in Net, that provides boilerplate for event sourcing constructs, or you might build it yourself using common libraries. Event store selection. For a greenfield project with high-volume expectations for enrollment and course progress, a dedicated event store like EventStoreDB might be chosen due to its performance, native event sourcing features, and support for subscriptions. For a smaller initial project, or if the team prefers familiarity, a well-structured SQL database table could serve as the event store initially. Domain service layer, a layer of services that orchestrate commands and interact with aggregates. For instance, an enrollment service would receive the enroll student in course command, load the relevant aggregates, apply the business logic, and persist the resulting events. Deployment. The right-side services, e.g., enrollment service, course service, identity service, would typically be deployed as independent microservices, each managing its own bounded context and event store, or sharing a central event store with separate streams. 4. Designing the read model architecture, CQRS in action. Since querying events directly for UI display is inefficient, we design specialized read models. This is where CQRS truly shines. User dashboard. For a student's personal dashboard displaying my courses, upcoming deadlines, and completed modules. Need fast lookup by studented denormalized overview. Read model data store. A document database like MongoDB or Couchbase, or even a SQL database with a highly denormalized table. Projections. An enrollment projection service subscribes to student enrolled event, enrollment completed event, course created event, etc. When student enrolled event occurs, it creates a new student enrollment view document for the student. When course created event occurs, from the course management context, it enriches the view with course details. When module completed event occurs, it updates progress in the student enrollment view. Course catalog search. For browsing and searching available courses. Need full text search, filtering, faceting, fast results. Read model data store, a search engine like Elasticsearch or Apache Solr. Projections. A course catalog projection service subscribes to course created event, course updated event, course published event. It indexes course details into Elasticsearch. Admin reporting, e.g., course enrollment trends. Need. Aggregated data, possibly complex analytical queries. Read model data store, a data warehouse, e.g., Snowflake, BigQuery, or a relational database with an OLAP-optimized schema. Projections. An analytics projection service consumes all relevant events, e.g., student enrolled event, enrollment completed event, and inserts updates, rows in fact and dimension tables for daily, weekly, monthly aggregation. Microservice intercommunication via events. Events from one bounded context can populate read models in another. For example, new user registered event from identity and access management might be consumed by the enrollment and progress context to set up an initial user progress record. Each of these read models is built by a dedicated projection service, consuming events via a message broker, e.g., Kafka. 5. Orchestrating complex processes with Sagas process managers. Many business processes in our online learning platform will span multiple aggregates and even multiple bounded contexts. Sagas are perfect for this. The course enrollment saga, trigger, enroll student in course command received by enrollment service leading to student enrolled event. Saga steps, enrollment service emits student enrolled event. Enrollment saga starts, listening to student enrolled event. Saga issues process course payment command to the payment component. Listens for payment processed event or payment failed event. If payment processed event, Saga issues grant course access command to the course access component. Listens for course access granted event. If course access granted event, Saga issues send welcome email command to the notification component. If any step fails, Saga issues compensating actions, e.g., cancel enrollment command, refund payment command. Implementation. Sagas can be implemented as state machines, often within their own microservice, a Saga service. They persist their own state, e.g., which step they are on, either in a small database or by event sourcing the Saga's state itself, often called Saga aggregates or process aggregates. 6. Infrastructure and deployment considerations. Putting it all together, the infrastructure glue is critical. Message broker, e.g., Kafka, essential for publishing events from the event store to all interested subscribers, read model projectors, Sagas, other services. Kafka's durability and replayability are invaluable here. Event store, as chosen earlier, e.g., EventStoreDB or SQLDB. A centralized event store or multiple event stores per bounded context. Read model databases, a mix of databases, MongoDB, Elasticsearch, PostgreSQL, as per the query needs. API gateway/frontend. For user interaction, typically a standard REST-TFL API or GraphQL endpoint that maps incoming requests to commands and queries the appropriate read models for display. Deployment. Each microservice, e.g., user account service, course catalog service, enrollment service, payment service, multiple projection services, Saga services would be deployed independently, potentially in containers Docker. Orchestrated by Kubernetes or managed cloud services, AWS ECS EKS, Azure AKS, Google GKE. Monitoring and tracing. Implement comprehensive logging, monitoring, and distributed tracing, e.g., OpenTelemetry, across all services and infrastructure components to maintain operational visibility. Propagation of correlationid and causationid is paramount. 7. Holistic design view. The complete architecture begins to look like a series of decoupled components, all communicating via events. Commands come in, generally via a REST API, processed by specific right-side microservices. Microservices contain aggregates. These aggregates process commands and emit events. Events go into event store, the immutable source of truth. Events are published via message broker, making them available to the rest of the system. Projection services consume events, building and maintaining various read models. Saga services consume events, orchestrating multi-step business processes, emitting commands in turn. API gateway/frontend queries read models for displaying data to users. This architectural style, driven by events, inherently promotes loose coupling, fault tolerance, and elasticity. Changes to one service, e.g., optimizing a specific read model, have minimal impact on others. Conclusion. Architecting an event-sourced application is a deliberate and iterative process. It begins with a strong foundation in domain-driven design, meticulously identifying events and commands, and thoughtfully choosing technologies for the right model, read models, and inter-service communication. By embracing CQRS and using patterns like Sagas for orchestration, you build a system that is not only robust and scalable, but also deeply aligned with your business processes. While it requires a different mindset and skill set, the resulting architecture offers unparalleled benefits in terms of flexibility, auditability, and adaptability to future business needs. In the next chapter, we will bring this design to life by walking through a practical implementation example. 9. Bringing it to life. Implementing event sourcing with a practical example. Understanding the theory and architectural blueprints is one thing. Seeing how it translates into executable code is another. In this chapter, we'll walk through a simplified, practical example of implementing event sourcing. Our focus will be on the core concepts: commands, aggregates, events, and their persistence in an event store. To keep the example accessible and clear, we will describe the components and their interactions verbally, much as you would explain them to a colleague, rather than using specific programming language code blocks. This approach emphasizes the conceptual flow transferable to any modern programming environment. Let's continue with our online learning platform example, specifically focusing on the course aggregate within the course management bounded context. Our goal is to implement the ability to create a course and update its title and description. Scenario: managing a course. Imagine a course instructor wants to create a new course, provide a title and description, update course details, change the title or description of an existing course. Step 1. Define the domain events. First, we identify the facts that will be recorded when something significant happens to a course. These are past tense, immutable occurrences. Course-created event signifies that a new course has been successfully initiated. Payload: course-id unique identifier for the course, title initial title, description initial description, instructor-id who created it, timestamp. Course title updated event signifies that a course's title has been changed. Payload: course-id old title, new title updated by timestamp. Course description updated event signifies that a course's description has been changed. Payload: course-id old description, new description updated by timestamp. Notice the detail in the event payloads. They capture the change, e.g., old title and new title, providing rich historical context for auditors or analytics. Step 2. Define the commands. Next, we define the imperative requests that a user, e.g., an instructor, would issue to initiate a change. Create course command: request to create a brand new course. Payload: requested unique ID for this command, suggested course-id optional for specific IDs, title, description, instructor-id. Update course title command: request to change an existing course's title. Payload: requested course-id new title updated by. Update course description command: request to change an existing course's description. Payload: requested course-id new description updated by. Each command also carries a requested for tracking and ensuring idempotency. Step 3. Model the aggregate, course. Now, we build our course aggregate. This is an object that encapsulates the course's core state and business rules. It will receive commands, apply business logic, and emit events. The course aggregate class would internally hold its course-id, title, and description. It would also track its current version number, representing its state after a certain number of events have been applied. Key methods on the course aggregate: constructor for new course, static course create course command. This is a factory method. It validates the command, e.g., title is not empty. If valid, it internally generates a course-created event with data from the command. It then applies this event to itself, setting its internal state, and returns a new course instance, ready to be persisted. Self-correction: a course should not be created if it cannot be identified. A unique ID is implicit or explicit in this step. Command handlers for existing course: void update title update course title command. Validation: checks if the new title is different from the current title. Ensures command.courseid matches its own courseid. Business rule: a potential rule might be: course title cannot be updated if the course is already published. If it's published, it would emit a course published event from a prior command. Event generation. If all valid, it internally generates a course title updated event, coursed, old title, new title, updated by, timestamp. It does not immediately change its internal title. Void update description, update course description command. Similar logic for description updates. Event application methods, internal appliers. These methods are private to the aggregate and are used to reconstruct its state from events. Void apply course created event sets the coursed, title, and description of the aggregate from the event payload. Sets version to 0 or 1 depending on convention. Void apply course title updated event updates the internal title to event new title, increments the version number. Void apply course description updated event updates the internal description to event new description, increments the version number. Step 4. The command handler and application service. When a create course command or update course title command arrives, it's processed by a course command handler. This handler acts as the application service layer. Process for create course command. Receives create course command from the API. Delegates to course create command. The course aggregate returns an instance, already having internally generated the course created event. The command handler takes this generated event and persists it to the event store. It then publishes the event to a message broker, e.g., Kafka, for other services to consume, e.g., red model projectors. Process for update course title command. Receives update course title command, e.g., for coursed. ABC 123. Load aggregate. It queries the event store for all events associated with coursed. ABC 123. Rehydrate aggregate. It loads an empty course aggregate object and feeds all fetched events to its internal apply methods, rehydrating it to its current state. For instance, if coursed ABC 123 has course created event and course description updated event in its history, the aggregate's internal state will reflect these changes. Execute command. It then calls course update title command. Event generation. If update title is successful, it internally generates a course title updated event. Optimistic concurrency check. Before persisting, the command handler checks the current version of the course aggregate, which was determined during rehydration, against the version number that the event store last recorded for this aggregate. This ensures no other concurrent operation has modified the aggregate since it was loaded. If there's a mismatch, it's a concurrency conflict, and the command might need to be retried. Persist event. The internal course title updated event is then delivered to the event store, which appends it to the coursed ABC 123 stream. The event store increments the stream's version. Publish event. The course title updated event is published to the message broker. Step 5. The event store interaction. Regardless of whether we choose a dedicated event store, like EventStoreDB, or a SQL database, the conceptual append operation is the same. When the command handler wants to save events, it performs an append operation. Event store append to stream, course ABC 123, expected version, new events. Course ABC 123, the name of the event stream for this specific aggregate. Expected version, the version of the stream the command handler expects to be committing against. This is crucial for optimistic concurrency control. If the expected version doesn't match the current version in the event store, meaning another process updated it concurrently, the append operation will fail and the command can be retried. New events. The list of newly generated events, e.g., course title updated event. Step 6. Implementing read models, CQRS. Remember, our UI needs to display a list of courses and their current details. For this, we'll build a course catalog read model. Database. Let's use a NoSQL document database like MongoDB for simplicity, as it handles denormalized data well. Projection service. A course catalog projection service will subscribe to events published on the message broker. On course created event, the projection service receives this event. It creates a new document in the courses collection in MongoDB. Id, coursed from event. Title, initial course title. Description, initial course description. Instructor, instructor name. On course title updated event, the projection service receives this event. It finds the document with id, coursed from event, and updates its title field to event new title. On course description updated event, similar update for the description field. Now, when the front-end application wants to display the course catalog, it simply queries this MongoDB courses collection, which is optimized for fast read access. The right-side event store and aggregates are left undisturbed. Step 7. Simplified request response flow summary. User action, instructor clicks update course title in the UI. API call. Front-end sends an HTTP post request to /API/courses/ABC123/title with new title, Math 101 Advanced. Command creation. The API layer translates this into an update course title command. Command handling. The course command handler receives the command. Aggregate rehydration. Course command handler fetches all events for course ABC 123 from event store, e.g., course created event, then course description updated event. State reconstruction. Course aggregate rehydrates itself by applying these fetched events, now holding calculus basics as its title and as description example data. Apply command, course update title, command is called. The aggregate validates, e.g., new title is different from current calculus basics. It internally stages a course title updated event, old title. Calculus basics, new title, Math 101 Advanced. Persist events. Course command handler tells the event store to append the course title updated event to the course ABC 123 stream, expecting the current version. If successful, the event is saved. Publish events. Course command handler publishes course title updated event to Kafka. 10. Read model update. The course catalog projection service, listening to Kafka, receives course title updated event. It finds its MongoDB document for course ABC 123 and updates its title. 11. Client notification, eventual consistency. The UI might initially query the read model and still see the old title for a split second. A common pattern is to either perform an immediate optimistic UI update based on the command result, or for the UI to subscribe to real-time updates from a WebSocket connected to the read model. This practical walkthrough demonstrates the mechanics of event sourcing and CQRS in action. While simplified, it highlights the clear separation of concerns, the flow of data, and the role of each component. It requires a different way of thinking compared to traditional CRUD, but it unlocks significant power through explicit history and flexible read models. In the next chapter, we'll delve into the crucial topic of ensuring the quality and correctness of such a system. Testing 10. Ensuring quality. Testing event source systems. Testing a traditionally built application might involve mocking database interactions and verifying API responses. For an event source system, with its inherent asynchronous nature, eventual consistency, and reliance on immutable event streams, the testing strategy needs to evolve. Without a robust testing approach, the advanced capabilities of event sourcing can quickly become a source of subtle bugs and operational headaches. This chapter outlines effective strategies for ensuring the quality, correctness, and resilience of your event-sourced applications. 1. The core principle: testing the business logic aggregates via events. The most fundamental shift in testing event-sourced systems comes from understanding that an aggregate's behavior is defined by the events it emits in response to commands. Therefore, the primary way to test an aggregate is to, given a certain initial state represented by a sequence of historical events, when a specific command is applied, then a specific sequence of new events should be generated or a specific error should occur. This approach aligns perfectly with behavior-driven development, BDD, principles, making it intuitive to write tests that directly reflect business requirements. Example for our course aggregate: Test case 1, successful course creation. Given no prior events for this course, i.e., an empty event stream, when a create course command is issued with title, introduction to event sourcing and description, learn the basics. Then, a single course created event should be emitted with title, introduction to event sourcing, description, learn the basics, and the correct course id. No errors should be thrown. Test case 2, updating an existing course title. Given a course created event for course ABC with title, old title, when An update course title command is issued for course ABC with new title. New title. Then, a single course title updated event should be emitted with old title and new title and the correct course ID. Test case 3. Invalid course update, business rule violation. Given a course created event for course XYZ with title, basic course, and a course published event for course XYZ. When an update course title command is issued for course XYZ with new title, advanced course. Then, an exception, e.g., course already published exception, should be thrown. No events should be emitted. This style of testing allows you to thoroughly test the aggregate's internal state transitions and business rules without relying on external dependencies like databases or message brokers. 2. Testing the persistence layer, event store integration. While aggregates themselves are tested in isolation, you need to ensure they can correctly interact with your chosen event store. Integration tests, write tests that verify event appends. Call the application service command handler to send a command, then read the events directly from the event store to confirm they were persisted correctly, in the right order, and with the expected data. Verify aggregate rehydration. Persist a known sequence of events to a temporary event store instance, e.g., an in-memory or Dockerized instance. Then, send a command that requires rehydrating the aggregate. Verify that the aggregate state is correctly reconstructed before processing the new command. Optimistic concurrency. Test scenarios where concurrent commands attempt to update the same aggregate to ensure proper optimistic concurrency handling, e.g., one succeeds, the other fails with a concurrency exception. These tests will typically use a real or mocked but faithful event store client and a lightweight database for the event store itself. 3. Testing read models, projections. Read models are derived from events, and their eventual consistency means they need their own testing approach. Projection unit integration tests. Given a set of events, e.g., course created event, course title updated event, when these events are processed by the projection service, then the read model database should contain the expected state. Full projection rebuild tests. It's crucial to be able to rebuild read models from scratch. Test scenario. Load a large set of events into your event store. Trigger a full rebuild of a read model. Verify that the rebuilt read model is consistent with the event history. This can be time-consuming but invaluable for operational confidence. Idempotency tests. Send the same event multiple times to a projection. Verify that the read model state remains correct, i.e., duplicated processing doesn't corrupt it. These tests often involve actual read model databases, e.g., an in-memory H2 database for SQL projections, or a test container for MongoDB/Elasticsearch. 4. Testing Sagas, process managers. Sagas orchestrate complex workflows responding to events and emitting commands. Testing them requires simulating the flow of events and commands correctly. Saga unit tests. Given the Saga is in a specific state, e.g., enrollment Saga is in seat-reserved state. When the Saga receives a particular event, e.g., payment failed event, then the Saga should emit specific compensating commands, e.g., release seat command, and/or transition to a new internal state, e.g., enrollment canceled. Simulate timeouts. Test Saga timeouts if applicable. Saga integration tests. These are higher-level tests that involve multiple aggregates and their services. Scenario. Drive a full business process via commands, e.g., enroll student in course command. Verification. Confirm that the Saga correctly orchestrates the sequence, including the generation of intermediate events and commands, and the final state of all involved aggregates. Failure scenarios. Crucially, test failure paths. Simulate a service failure, e.g., payment service returning an error. Verify that the Saga triggers the correct compensating actions. These tests can be complex, often requiring a framework-level test harness that allows injecting events and capturing emitted commands. 5. Higher-level testing, end-to-end and performance. End-to-end E2E tests. While detailed component testing is vital, E2E tests provide confidence that the entire system functions as expected. Scenario. User interacts with the UI, which sends commands. The eTWI test then queries the relevant read model via the API to assert the expected outcome. Challenge with eventual consistency. eTWI tests need to handle the eventual consistency of read models. This often means polling the read model until the expected state is achieved within a reasonable timeout. Performance testing, write throughput. Test the event store's ability to handle anticipated command rates and event appends per second. Read model latency. Measure the query response times of your read models under load. Event processing latency. Monitor the lag between events being published and consumed by projections and Sagas. Scalability testing. How does the system perform as you scale up event producers and consumers? 6. Tooling and test harnesses. Effective testing of event source systems benefits significantly from specialized tooling. Event sourcing frameworks. Many frameworks provide built-in test fixtures for aggregates, command handlers, and Sagas, simplifying test setup and assertions. In-memory event stores. For unit and integration tests, using an in-memory or lightweight mock event store, e.g., a list of events, significantly speeds up testing. Test containers. For more realistic integration tests, use Docker test containers to spin up real databases, event store, read models for each test run, ensuring isolation and consistency. BDD frameworks. Tools like Cucumber, Many Languages, SpecFlow.net, or JBehave Java can help structure those given when then tests effectively. Best practices for testing. Test your business logic, not infrastructure. Focus the majority of your tests on the aggregates and Sagas as they encapsulate your core business rules. Infrastructure interactions, event store, message broker, can be tested at a higher integration level. Small, focused tests. Keep unit tests granular and focused on a single behavior. Clear test data. Use simple, clear event sequences to set up test scenarios. Automate everything. Integration tests should be part of your continuous integration (CI) pipeline. Reproducible tests. Ensure tests are independent and can be run in any order without side effects. Living documentation. Well-written BDD-style tests serve as excellent, always up-to-date documentation for your system's behavior. Conclusion. Testing event source systems demands a deliberate shift in perspective and methodology compared to traditional CRUD applications. By focusing on the immutable nature of events, leveraging BDD, and strategically employing different levels of testing, from aggregate units to full system integration, teams can build high confidence in the quality and correctness of their event-driven solutions. While the initial investment in adapting testing practices might seem significant, it pays dividends in avoiding costly runtime issues and ensuring the long-term maintainability and reliability of your event-sourced application. With testing under control, we turn our attention to the operational realities of living with event sourcing. 11. Living with event sourcing. Operational concerns and scalability. Building an event source system is one thing. Successfully operating it in production at scale is another. The unique characteristics of event sourcing and its symbiotic relationship with CQRS and event-driven architectures introduce specific operational challenges and considerations for scalability. This chapter delves into the practical aspects of running, monitoring, and scaling your event-sourced application, ensuring its longevity and performance. 1. Operational realities of the event store. The event store is your system's single source of truth. Its operational health is paramount. High availability and disaster recovery. Clustering. Implement a clustered event store solution, e.g., EventStoreDB cluster, Kafka cluster, highly available SQL database. This ensures that if one node fails, the system remains operational. Replication and backups. Implement robust data replication strategies and regular backups. For mutable databases, point-in-time recovery is standard. For append-only event logs, ensure continuous archiving or snapshots are taken. Data center strategy. Consider active-passive or active-active multi-data center deployments for ultimate disaster recovery, particularly for geo-distributed systems. Monitoring and alerting. Latency, crucial metric. Monitor event append latency and event retrieval latency from the event store. High latency signals potential bottlenecks. Throughput. Track events per second being written and read. Set thresholds to alert on unexpected drops or surges. Storage growth. Event stores grow indefinitely. Monitor storage consumption and anticipate future capacity needs. Implement alerts for disk space nearing limits. Version conflicts. Track concurrent update conflicts on aggregates. While normal in a distributed system, a high rate might indicate a design flaw, e.g., aggregate too large, too many commands targeting the same hot aggregate. Infrastructure metrics. CPU, memory, network I/O of the event store servers. Version upgrades and maintenance. Plan for zero downtime upgrades of your event store infrastructure. Understand how your chosen event store handles schema migrations and data transformations during upgrades. 2. Managing read model lifecycles. Read models are secondary data stores, but critical for application responsiveness. Monitoring projection lag. This is arguably the most important metric for read models. Monitor the delay, lag, between events being written to the event store and their appearance in the respective read model. A constantly increasing lag indicates a projection service struggling to keep up. Projection rebuilds. Operational procedure. Have a well-documented and automated procedure for rebuilding read models from scratch. This is often needed for bug fixes in projection logic, schema changes, or disaster recovery. Impact. Understand the performance impact of a full rebuild on the event store, increased read load, and the projection service, reprocessing all historical events. Consider a blue-green deployment model for read models during rebuilds to avoid downtime. Schema evolution. Coordinate red model schema changes with event schema evolution. An event schema change often necessitates a read model schema change and a rebuild. Read model scalability. Read models should scale independently. Use distributed databases, e.g., sharded MongoDB, clustered Elasticsearch, or replication, e.g., PostgreSQL replicas, to handle high read loads. 3. Event management and lifecycle. Events are immutable, but their management isn't static. Event retention and archiving. Indefinite storage. The primary event store should retain events indefinitely as they are the absolute source of truth. Archiving to cold storage. For very high-volume systems, consider offloading older, less frequently accessed events to cheaper, long-term cold storage, e.g., S3, Google Cloud Storage, Azure Blob Storage. The event store would then only retain a working set of events. Data deletion, GDPR, right to be forgotten. This remains a significant challenge. As discussed in Chapter 7, strategies include encryption of PII in event payloads with key deletion, or data redaction nullification in derived views projections, rather than physical deletion of events. Event exploration and debugging tools. Provide tools for operations teams to inspect event streams, search for specific events by ID or type, and potentially replay specific sequences. Visualizers for event flows can be invaluable. Event versioning management. Ensure a clear process for introducing and deploying new event versions and managing their upcasters. Keep event schemas as stable as possible to minimize upcaster maintenance. 4. Scalability strategies. Event sourcing inherently promotes scalability due to its write-read separation and asynchronous nature. Write-side scalability. Event store scalability. As mentioned, scale the event store to handle your throughput. Horizontal scaling capabilities are available in dedicated event stores or Kafka. Aggregate concurrency. Identify hot aggregates, those receiving very frequent commands. If an aggregate becomes a bottleneck, e.g., many concurrent commands hitting a single product inventory aggregate, explore strategies. Decomposition. Can the aggregate be split into smaller, more granular aggregates? E.g., product inventory item for each specific batch or location. Command batching. For certain scenarios, batching commands can reduce contention. Command queue. Ensure robust command queuing for retriability if optimistic concurrency conflicts occur. Read-side scalability. Independent scaling. Read models can easily scale independently of the write model. If a particular dashboard is getting heavy traffic, you can add more instances of its projection service and/or scale up its dedicated database. Caching. Implement robust caching layers, e.g., readies in front of your read models for frequently accessed data. Asynchronous processing. The reliance on message brokers for event propagation naturally decouples producers and consumers. This allows components to operate at their own pace and absorb bursts of activity. Scale message broker throughput and consumer group instances as needed. Microservices as the default. Event sourcing naturally encourages microservices. This allows for independent development, deployment, and scaling of specific business capabilities. 5. Monitoring a distributed system. Operating an event-sourced, CQRS-based microservices architecture requires strong observability. Distributed tracing, crucial. Tools like OpenTelemetry, Jaeger, or Zipkin are indispensable. They allow you to trace a single command from the API gateway through the aggregate processing, event persistence, event publication, red model updates, and Saga orchestrations. This helps pinpoint latency and error sources. Centralized logging. Aggregate logs from all services and infrastructure into a centralized system, Elk Stack, Splunk, Datadog. Ensure logs are tagged with correlationed to link related events. Metrics aggregation. Collect metrics, latency, error rates, throughput, resource utilization from all services and infrastructure components using tools like Prometheus/Grafana or cloud monitoring services. Transaction monitoring. Beyond individual component health, monitor the success and failure rates of key business transactions, e.g., course enrollment complete end-to-end, even if they span multiple services. 6. The ops mindset shift. Traditional operations teams are used to monitoring databases and application servers. Event sourcing adds new layers. Understanding event flow. Operations teams need to understand the event flow, where events originate, where they go, and how they get consumed. Event store specifics. Expertise in operating the chosen event store technology. Troubleshooting distributed systems. Diagnosing issues in an asynchronous, eventually consistent system. Where is my data? Becomes, where is my event currently in the pipeline? Replay capabilities. The ability to replay historical events into a test environment to reproduce and debug production issues. Conclusion. Living with event sourcing means embracing a different operational paradigm. While the benefits in terms of auditability, scalability, and flexibility are profound, they come with the responsibility of meticulously managing your event store, continually monitoring your read models, and fostering a deep understanding of distributed system dynamics within your operations teams. By proactively addressing these concerns, leveraging robust tooling, and adopting a strong observability culture, you can ensure your event-sourced application not only thrives in production, but also adapts and scales effectively with your evolving business needs. Our journey through event sourcing is nearing its end. In the final chapter, we'll cast our gaze into the future, exploring how event sourcing continues to shape the landscape of software architecture. 12. The future is event-driven. Beyond the horizon of event sourcing, we have embarked on a comprehensive journey, exploring the why, how, and what if of event sourcing. We've dissected its core components, understood its powerful design patterns, confronted its challenges head-on, and walked through its practical implementation and operational realities. As we reach the culmination of this exploration, it's clear that event sourcing is more than just a persistence pattern. It's a fundamental shift in how we perceive and manage data, placing historical record and business intent at the core of our systems. But where does event sourcing fit in the broader landscape of software architecture? What does its future hold, and how might it continue to shape the way we build applications? Not a silver bullet, but a powerful tool. Let's begin by reiterating an important point. Event sourcing is not a panacea that should be applied to every software problem. For simple CRUD applications with minimal auditing requirements, where immediate consistency is paramount and historical context is irrelevant, the overhead of event sourcing and CQRS might introduce unnecessary complexity. Choose event sourcing when auditability is paramount. You need a complete, unalterable record of everything that has ever happened in your domain. Temporal queries are important. The ability to time travel and reconstruct past states is a business requirement. Business intelligence from history is critical. You want to derive rich insights from historical data for analytics, machine learning, or complex reporting. High scalability and flexibility for reads are needed. You benefit from separating read and write concerns, potentially with highly optimized, different read models. Complex business processes require orchestration. Sagas are invaluable for distributed transactions. Your architecture is embracing microservices. Events are the lingua franca of loosely coupled services. When these conditions apply, event sourcing transitions from a technical curiosity to a profoundly enabling architectural paradigm. The rise of event-driven architectures and data mesh. Event sourcing is a key enabler for the broader trend of event-driven architectures, EDA. In an EDA, services communicate primarily through events, leading to inherently decoupled, scalable, and resilient systems. As organizations continue to move towards microservices and distributed systems, the importance of robust eventing mechanisms and event-first thinking will only grow. Beyond traditional application boundaries, the concept of data mesh is gaining traction. Data mesh views data as a product, owned by domain teams, and served to consumers through discoverable, addressable, trustworthy, and interoperable datasets. Event streams, naturally flowing from event source systems, are perfectly positioned to serve as these data products, directly exposing business facts to data scientists, analysts, and other applications without requiring complex ETL processes from operational databases. The event store becomes a powerful, real-time data source for the entire enterprise. Advancements in tooling and ecosystem. The event sourcing ecosystem continues to mature. Dedicated event stores like EventStoreDB are becoming more robust, performant, and feature-rich, offering better tooling for operations and development. Frameworks and libraries across various programming languages are simplifying the implementation of event sourcing patterns, abstracting away much of the boilerplate and allowing developers to focus on domain logic. Cloud providers are offering managed services that facilitate event streaming and data processing, reducing the operational burden. As the tooling improves, the barriers to entry for adopting event sourcing will gradually lower, making it more accessible to a wider range of teams and projects. The blurring lines, operational and analytical data. Traditionally, operational databases for day-to-day transactions and analytical databases for business intelligence have been separate worlds. Event sourcing, with its immutable log of business facts, naturally blurs these lines. Real-time analytics. Event streams enable real-time analytics and dashboards, providing immediate insights into business operations. Machine learning. The rich historical context in event streams is invaluable for training machine learning models, offering a nuanced view of how systems and users behave over time. Operational intelligence. The audit trail inherent in event sourcing allows for powerful operational queries directly on the event stream, enabling deep post-mortem analysis and debugging. The event store can truly become the central nervous system for both transactional processing and deep analytical insights. Overcoming remaining challenges. While progress is undeniable, some challenges persist and will continue to drive innovation. Data governance and PII. The right to be forgotten in an immutable event log remains a complex issue. Future solutions may involve more sophisticated cryptographic event redaction, tokenization, or secure multi-party computation over encrypted event streams. Read model management at extreme scale. As event volumes grow exponentially, managing hundreds or thousands of projections and ensuring their consistent performance will necessitate new patterns for automated orchestration and lifecycle management of derived views. Standardization. While patterns are emerging, more industry-wide standards for event formats, event stream discovery, and inter-service communication would further accelerate adoption and interoperability. A mindset for the future. Ultimately, event sourcing champions a mindset of facts over current state, history over mere snapshots, and change as a first-class citizen. This mindset is intrinsically aligned with the needs of modern, complex, and data-intensive applications. It's about building systems that remember not just what it is, but how it came to be, empowering deep understanding and unprecedented flexibility. As software continues to eat the world, the demand for systems that are resilient, auditable, scalable, insightful, and adaptable will only intensify. Event sourcing, with its elegant approach to capturing the narrative of our domains, is poised to remain at the forefront of software architecture, enabling us to build the intelligent, history-aware applications of tomorrow. The journey into event sourcing is a transformative one. It challenges established norms, but rewards those who embrace its principles with remarkably powerful and insightful systems. May your event streams flow richly, and your historical data illuminate the path forward.